Welcome to our series on radome and bumper testing, where we cover everything you need to know about radome testing and the usage of the powerful QAR50. This video is about the instrument's resolution and capability to distinguish between different potential sources of irregularities inside the radome. To start with, let us have a look on the definition of resolution. Let's start with the definition for a radar. So on the left-hand side, you can see the typical receiving plot of a radar, where we have the distance on the x-axis and the amplitude of the received signal on the y-axis. In this case, we have one clear target, which is at a certain distance d, and we see that this target is clearly speaking out of the noise. So we can clearly say this is where the target is. So the accuracy of target detection here is quite high because we only have one target. Now there's a second target. So when we move to the right-hand side, you can see there's not only one peak, but there's now two peaks. So how can we distinguish between the two peaks? And what kind of level drop do we need in between those two peaks in order to clearly distinguish them? So for the radars, it has been defined that in order to distinguish between two targets, there need to be a 3 dB drop between these two targets. So that's simple to define amplitude. Now, how do we define that for the QAR50? So in the QAR50, we measure the phase resolution. So that means we are measuring the phase and no longer the amplitude as we did for the radar. As well, we have actually a two-dimensional plot, but it's the same as with the one dimensions we explain here. So let us, for simplicity, stick with that one direction. On the left-hand side, we see that typical one target again, where we can clearly see one target. On the right-hand side, we have the same plot with the phase, and we say, okay, the phase difference between the peak and the drop in between the two peaks needs to be 3 dB. The problem is, what is actually 3 dB in phase? Because that's not clearly defined. So we had a really hard time to define what is the resolution of the QAR50 because there's no such definition for phase resolution available. So when we look into the datasheet, what did we actually come up with? So here you see the line image lateral resolution, which is depicted as smaller than 8 millimeters. So how did we get to these 8 millimeters if we, so to say, don't know what to actually do? Therefore, we have prepared different foils with different cutouts. So in this case, I have a foil with a cutout of 60 millimeters in the middle and different cutouts here on the left-hand side and on the right-hand side. There's another one of those foils inside the instrument. So the foils have a thickness of around about 190 micrometers and they cause a phase change of about 14 degrees. So we want to see how small can we make the cutouts in order to still be able to distinguish between them in the QAR50's image. So on the left-hand side, you see the theoretical drawing of what we are putting there, and on the right-hand side, you see the expected measurement result. So the green line is depicting the, so to say, ideal result with 0 millimeters resolution, and the red line is depicting the measurement result with a certain resolution. So theoretically, we have these cutouts and we would expect the phase change of 40 degrees to immediately happen of the exact same position where the cutout is. Due to physics, this will never happen. The question is, how close will we get to this ideal behavior? So if we have a look at this 8 millimeter plate, which is the one which is currently in the instrument, we can see in the middle of the screen that we can more or less distinguish between the three cutouts. Also on the right-hand side, you see the theoretical behavior of the phase, and you see what the QAR50 is actually measuring. So for this 8 millimeter sample, we can clearly distinguish between these cutouts, and we think this is, so to say, a worst case scenario for the QAR50, and therefore stated that the QAR50's resolution is about or better than 8 millimeters. So how does that look with the different cutouts that we have prepared? So this is depicted on that slide. It's showing a summary of the different measurement results. Again, the phase mask image on top and the two-dimensional representation of the center on the bottom. So If we have bigger cutouts, for example, the slits with 24 millimeters on the left, we can see we are pretty much close or more or less close to the ideal behavior. And the smaller the slits get, the smaller also the face gets that we measure with the QAR50. So on the right-hand side, again, so to say the border case where we have the 8 millimeter slits, which is roughly the resolution of the instrument. So just for curiosity, we have performed the same measurement as well with the vector network analyzer in our quasi-optical setup. Of course, we don't have any kind of phase resolution there, so we can't expect to be able to distinguish between these slits there. The question is just, what will we see? And these are the results of the exact same foil with the vector network analyzer. And we can see with the infinite slit size, we have around 16 degrees of phase. And with the 8 millimeters, we have 22 degrees of phase. Full sheet has 30 millimeters of phase. So why does the infinite line also have a phase? The reason is we are using this Arex in order to correctly position these slits. So this also has a phase, and therefore we are not starting at 0, but we are starting at a certain offset, but it doesn't really alter the effect. So again, here we see an effect, but it's not really clearly distinguishable, and we also don't get any resolution. So we see something on the VNA, but we see much more on the QAR50, and that is how we defined the resolution.